Hello students, so continuing our lectures on solid state physics, today we'll start with NSL structure, and it is basically two interpenetrating FCC lattices with chlorine at 0, 0 and 0 and sodium ion at 0.5, 0.5 and 0.5, and its nearest neighbor is 6, and examples are NaCl, lithium hydride, manganese oxide and magnesium oxide. Similarly, we have a cesium chloride structure where instead of an interpenetrating FCC we have an interpenetrating simple cubic structure with cesium and chloride at its pooling positions. Like in this case, the cesium is at the corners and chlorine is at the center, and the nearest neighbors are 8 numbers, and examples are cesium chloride, beryllium, copper, aluminum nitride, copper, zinc, copper, palladium, and AgMg, silver, magnesium alloys. Next is your HCP, which is the closest possible packing, and it's an hexagonal lattice with 2 atoms bases, and it looks something like this. There is a 2 atom basis at the center, and the basis atom at 0, 0, 0 and 2/3, 1/3 and 1/2. And this is important, 2/3, 2/3, 1/3 and 1/2. This value is important, and examples are helium, beryllium, magnesium and titanium. Next we have the diamond structure. The examples, all semiconductors actually fall into this structure, and examples are silicon and germanium. So there are FCC lattices with 2 atoms primitive basis. The bases of the atoms are at 0, 0, 0, 0.25, 0.25 and 2.55. So this is also important. So 2 atom forms a 2 atom primitive basis, which is quite interesting. And then we have the zinc blende structure, and these are the examples: zinc sulfide, aluminum fluoride, silicon carbide and aluminum fluoride. And again there are 2 FCC lattices displaced from one another. So this property, that although there are 2 interpenetrating lattices as in the case of NaCl, but they are displaced from one another by the following values, and they make a regular tetrahedron with 4 nearest neighbors. Okay, so these are the different type of structures. Now we move on to the periodicity of a lattice. So any one-dimensional periodicity of A can be expressed in this following Fourier series. This is P and SCP are the Fourier constants. So this 2 pi by A is again, it ensures that there is a periodicity in A. So that means if we increase the value by an A, which will go a little bit of translation, so that we will get back the same value. This is what is the periodicity. Now this value, this value, it is a point in the reciprocal lattice. So if we do the Fourier transform, again this NP is generally complex numbers, and with P is and all positive integers, positive and negative. So we are talking about this P, this P. So reciprocal. So this is how this it ensures that Nx is real. Nx n pi star is equal to Np, ensuring real, and this is actually a phase. 2 pi x pi, it is actually a phase. So this is how this periodicity is defined. Now this is where the reciprocal lattice comes into the picture. This is a very well known vector. The reciprocal lattices are given as v1, v2 and v3, where v1 is a2 cross a3 by a1 dot a2 cross a3, variable, and that is same goes for v2 and v3. And the property of reciprocal lattice is bi dot ai is 2 pi ij, and these are the two properties. And when there is a translation taking place, I think this is where the translation taking place, we are getting this value. So the extra term that we get is this one. Initially it was only gi by r, so by using this translation, the extra term is I dot g is equal to t, and so this has to be equal to 1 to make the theorem correct. So to ensure that there is a periodicity, so this is what we get. So there are two terms. First of all, is g by t is equal to 2 pi by 2 pi m, and bi dot ai is equal to 2 pi. This is the two conditions for the reciprocal lattice, and this is actually the reciprocal lattice vector g.